Chapter number 15, Polymer. Today we are going to revise about polymers. First we will see overview of the polymers, then we will discuss the preparation, properties and uses of polymers by animation. So animation will be there after this overview of the polymers. Okay, so polymers are classified on the basis of source or origin, structure, molecular forces and synthesis. So based on source, the polymers are classified in three categories. Based on source, polymers are classified in three categories. First is natural polymer, second is semi-synthetic polymer, and third is semi-synthetic polymer. Semi-synthetic polymer. Okay. Now, next classification is based on structure. So based on structure, polymers are classified in three categories. First is linear polymer, second is branch polymer, and third is cross-link polymer. Cross-link polymer. Okay. Now third classification is based on molecular forces. Based on molecular forces. Based on molecular forces, polymers are classified in four categories. First is elastomer. Second is fibers. Third is thermoplastic. And fourth is thermosetting plastic. Okay. Now next classification is based on type of polymerization. Or based on synthesis. Based on type of polymerization or based on synthesis. So based on type of polymerization, there are mainly two type of polymers. First is addition polymer and second is condensation polymer. Okay. In addition polymers, there are two types: homopolymer and second is copolymer. Okay. Now we have already discussed about these polymers, so we will only revise the name of polymers and then preparation will be discussed in animation. Okay, so addition polymers are: first is polythene, second is polythene mainly LDP, second is SDP, third is Teflon, fourth is polyacrylonitrile, that is PEN. Okay, whereas condensation polymers are: first is polyamide category, that is nylon 66, second is nylon 6, third is dacron or terylene, next one is bakelite and melamine. So these are the addition and condensation polymers we have already discussed till now. Then we had discussed about rubber. In case of rubber, we had discussed about preparation of synthetic rubber, preparation of natural rubber, and we have natural rubber, and we had discussed about vulcanization of rubber and importance of vulcanization. So till now we have discussed these many topics. Now we are going to see these polymers in detail by animation.
And their uses. Some important addition polymers are low-density polythene, high-density polythene, Teflon, and polyacrylonitrile. Let's look at each in turn. Low-density polyethylene or polythene is often given the acronym LDPE. To obtain LDPE, it is necessary to polymerize ethene under high pressure in a temperature range of 350 to 570 Kelvin in the presence of a catalyst. Typically, either oxygen or a peroxide initiator, such as benzoyl peroxide, is used as a catalyst. The equation shown here represents the polymerization reaction to form LDPE. LDPE is a highly branched structure, where the branches in turn may also have side chains. The branches keep the chains from packing closely together, and so the resulting plastic is soft. LDPE is chemically inert. It is tough but flexible and a poor conductor of electricity. LDPE is used to make insulation for electrical wiring, besides squeeze bottles, toys, and flexible pipes. High-density polythene or polyethylene, also known as HDPE, is another polymer made from ethene monomers. To make HDPE, ethene is reacted in a hydrocarbon solvent in the presence of a Ziegler-Natta catalyst at a low temperature of 333 to 343 Kelvin and a high pressure of 6 to 7 atmospheres. A Ziegler-Natta catalyst is a combination of triethyl aluminium and titanium tetrachloride. When triethyl aluminium and titanium tetrachloride are mixed in a hydrocarbon solvent, a heterogeneous precipitate forms, which catalyzes polymerization of alkenes like ethene. The catalyst that results has an empty orbital on titanium, which can form a complex with double bond in ethene. These reaction conditions lead to linear molecules that are closely packed together with a high overall density. HDPE is tough and hard. It is used to make buckets, dustbins, bottles and pipes, among other things. Teflon is another example of an addition polymer. The structure of Teflon is shown here. Can you determine the structure and the name of the monomer used to make Teflon? Since Teflon is an addition polymer, it suggests that the monomer contains a carbon-carbon double bond and 4 fluorine atoms. The monomer used to make Teflon is tetrafluoroethene. The overall equation for the polymerization reaction is shown here. Teflon is the trade name for polytetrafluoroethene. To make Teflon, tetrafluoroethene is heated with a free radical or persulfate catalyst at high pressures. Teflon is chemically inert and resistant to attack by corrosive substances. Teflon is used to make oil seals and gaskets. It is extensively used to make non-stick cookware. Teflon coatings decompose at temperatures above 300 degrees Celsius. So, don't use non-stick pans at high heat. Be careful not to scratch the coating and replace pans when the Teflon coating is damaged. Another important addition polymer is polyacrylonitrile. This polymer is formed by polymerizing acrylonitrile in the presence of a peroxide catalyst. The overall reaction is shown here. Polyacrylonitrile produces the commercially important acrylic fiber. The trade names for acrylic fibers include Orlon and Acrylan. These acrylic fibers are soft and flexible and produce lofty yarns. These properties of acrylic fiber closely resemble those of wool. Hence, acrylic fibers are often used to make sweaters and other pieces of apparel. Acrylic fibers have good resistance to stains, chemical, insects, and fungi. Can you write the chemical equation that represents the formation of polystyrene from styrene? The formula for styrene is given here. Polystyrene is an addition polymer. This can be inferred from the carbon-carbon double bond in styrene. Polystyrene is commonly referred to as styrofoam. In condensation polymerization, the molecules of a monomer combine with the elimination of simple molecules such as water, alcohol, and ammonia to form a polymer. The polymer so formed is called a condensation polymer. You already know that condensation polymers are the result of repeated condensation reactions between two different bifunctional monomers. Hence, this type of polymerization also involves a series of reactions, just as in addition polymerization, but it differs in the aspect that each step is independent of the preceding one. The series of reactions in condensation polymerization is attributed to the presence of more than one functional group in the monomer. In other words, the formation of a polymer is possible as the monomer can undergo reaction at more than one functional group. The product formed in each step of the reaction as a result of condensation between two different bifunctional monomers also has a bifunctional group that can further react with another monomer to form a larger molecule. The series of such reactions continues. The stepwise condensation of monomers, which results in the formation of a polymer, is called step growth polymerization. Illustrated here is the condensation reaction between ethylene glycol and terephthalic acid polyethylene terephthalate, PET, also known as Dacron. Note that in each step, when two different monomers combine, a water molecule is eliminated. Let us now see how some important condensation polymers are prepared and their uses. polyamides, polyesters, phenol formaldehyde polymers, and melamine formaldehyde polymers are all important condensation polymers. Polyamides are polymers that have amide linkages. Polyamides may be naturally occurring, such as proteins, or synthetic, such as nylons. Nylons are commercially important synthetic fibers. The general reaction to obtain polyamides can be described as the reaction of diamines with dicarboxylic acids or dibasic acid to form amide linkages. Several different forms of nylon have been synthesized. One important nylon polymer is nylon 6,6. To obtain nylon 6,6, adipic acid or 1,6-hexane-dioic acid is made to react with hexamethylene diamine or 1,6-diaminohexane at a high temperature of 553 Kelvin and high pressure. This polymer is called nylon 6,6 because there are 6 carbon atoms in each monomer, adipic acid and hexamethylene diamine, that participates in the reaction. Nylon 6,6 is used to make sheets, bristles for brushes, textiles, and tire cord. Nylon 6, another synthetic fiber, resembles the properties of nylon 6,6 closely. To obtain nylon 6, caprolactam is subjected to prolonged heating with water at a high temperature of 533 to 543 Kelvin. Nylon 6 is known by its trade name, Perlon L. It is used to make tire cords, fabrics, and ropes. Polyesters are another important group of condensation polymers. The general reaction to obtain a polyester is a condensation reaction between a dicarboxylic acid and a diol. Dacron is the trade name for polyethylene terephthalate, or PET, a common polyester. To make dacron, ethylene glycol and terephthalic acid are reacted at 420 to 460 Kelvin in the presence of a zinc acetate, antimony trioxide catalyst. The structure of the repeating unit is shown here. Dacron is crease resistant. Therefore, it is often blended with cotton and/or wool. It is also used as glass reinforcing material in safety helmets. Can you write the equation for the formation of Kevlar via a condensation reaction from the monomers shown here? These two monomers can form a polyamide chain with para or 1,4 linkages. Notice that HCl is formed during the condensation reaction. Kevlar fibers are very strong as many hydrogen bonds are present between the chains, as shown in the illustration here. Kevlar is used to make protective gear, including bulletproof vests. It is also used to make a variety of sports equipment, including boats and tennis rackets, besides puncture-resistant bicycle tires. Phenol formaldehyde polymers are another important group of condensation polymers. The first step to produce a phenol formaldehyde polymer is the condensation reaction of phenol with formaldehyde in the presence of an acid or a base catalyst. This results in the formation of ortho and or hydroxymethylphenol as shown in the equation. In the subsequent steps, the hydroxymethylphenol derivatives react further with phenols to form polymers with rings joined by CH2 groups. For example, the linear structure shown here, known as novolac, is used in paints. When novolac is heated with formaldehyde, many cross-links between the chains develop. This cross-linked, rigid three-dimensional structure is called bakelite, the first synthetic polymer that was ever developed. Bakelite can be used to make combs, phonograph records, electrical switches, and utensil handles. Bakelite is also used as a porcelain substitute, such as in game pieces. Another important condensation polymer is the melamine formaldehyde polymer. The first step in the formation of this polymer is the reaction between melamine and formaldehyde, which results in the formation of a resin intermediate. The resin intermediate undergoes condensation polymerization to form melamine. Melamine is used to make unbreakable crockery. It can chip and scratch. However, it is not microwave safe. Melamine is also used to make fireproof jackets. Note that both bakelite and melamine are thermosetting polymers. Copolymerization is a type of polymerization reaction in which more than one kind of monomers polymerize to form a copolymer. Copolymers can be obtained by either chain growth polymerization or step growth polymerization. You already know that in contrast to copolymers, homopolymers are obtained by the polymerization of a single monomeric species. Here is a problem for you to try based on this concept. Identify the structures here as either a homopolymer or a copolymer. Structure A is a butadiene-styrene copolymer, BUNA-S. The monomers used are 1,3-butadiene and styrene. Structure B is a homopolymer, polystyrene. It is made from styrene monomers. Let us now understand how the properties of a copolymer differ from that of a homopolymer with a suitable example. BUNA-S, a butadiene-styrene copolymer, is elastomeric and tough, as in this bicycle tire. In contrast, polystyrene, a homopolymer, is brittle. As a mixture of two or more different monomers undergoes copolymerization, the copolymers produced have better physical and mechanical properties than homopolymers. For instance, the copolymerization of styrene with butadiene adds toughness, and with acrylonitrile enhances resistance to impact. The butadiene-styrene copolymer finds use in the manufacture of automobile tires, floor tiles, footwear components, and cable insulation. Let us now study rubber and elastomer in detail. Natural rubber is a polymer with elastomeric properties. It is obtained from the bark of the rubber tree in the form of latex. Rubber latex is a colloidal dispersion of rubber in water. Isoprene 2-methyl-1,3-butadiene polymerizes to form cis-1,4-polyisoprene, which is natural rubber. Thus, natural rubber is a linear polymer of 2-methyl-1,3-butadiene. The chains are held together by weak van der Waals interactions, and hence it is elastic and non-crystalline. The polymer chains form a coiled structure. Natural rubber can be stretched. When stretched, the chains get aligned in the direction of the external force. When the external force is released, the chains snap back to their original positions. Untreated natural rubber is quite sticky. It becomes soft at high temperatures, greater than 335 Kelvin, and brittle at low temperatures, less than 283 Kelvin. Natural rubber absorbs water. It is soluble in non-polar solvents and is susceptible to attack by oxidizing agents. These properties of natural rubber limit its usefulness. Hence, to improve the physical properties of natural rubber, a process called vulcanization is employed. Most rubber used today is vulcanized rubber. To vulcanize rubber, raw rubber is mixed with sulfur and heated between 373 and 415 degrees Kelvin. This forms sulfur cross-links at the reactive sites of double bonds, such as allylic positions, and thus the rubber gets stiffer. Commercially, other substances called accelerators and activators are added to enhance the quality of the rubber. Let's look at the possible structures of vulcanized rubber. Notice the sulfur cross-links between the chains. The vulcanization process is generally irreversible. The cross-links help vulcanized rubber to maintain its shape when stretched. Vulcanized rubber is not very sticky, unlike natural rubber. Vulcanized rubber has high tensile strength and is usable over a wide temperature range. It is also resistant to abrasion. Vulcanized rubber has many uses. Perhaps its best known uses are car tires and shoe soles. Synthetic rubbers have also been developed. These are more flexible, tougher and durable than natural rubber. Synthetic rubber can be defined as any rubber-like polymer that can be vulcanized. Synthetic rubber must be elastomeric. It can be stretched and then must return to its original shape. Neoprene is an example of a synthetic rubber. This homopolymer is made from a monomer that is a 1,3-butadiene derivative, chloroprene. Chloroprene undergoes free radical addition polymerization to form neoprene. Neoprene is resistant to vegetable and mineral oils. It is used to manufacture conveyor belts, gaskets, and hoses. It has a wide variety of household and recreational uses as well. Another important synthetic rubber is Buna N, also known as nitrile rubber. It is a copolymer of 1,3-butadiene and another unsaturated monomer, acrylonitrile. A peroxide catalyst is required for the reaction. The overall equation is shown here. Buna-N or nitrile is resistant to petrol, lubricating oil and organic solvents. It can be used over a wide temperature range, and so it has many applications in automobiles. Buna-N is used to make oil seals and tank linings. Non-latex